Last week, we were working on coding, Python coding. We were introducing Python coding. Some of you may already be very familiar with Python coding, but it was aimed at if you're not familiar with Python coding. So I think of that as coding week. This week, we're going to be talking about data. We're going to be talking about reading data. We're going to talk about analyzing data, simulating data, and visualizing data. So it's sort of data week this week. And it'll be next week we get on to the big physics problems that we're gonna go ahead and solve. Just as a summary, last week we met the important components of Python that we need: assignments and arithmetic in Python, control and flow in Python, functions, native functions, library functions in Python, and some simple input output. We talked about the application to the gravitational many-body differential equation problem. We talked about how simple analytical solutions of the gravitational many-body differential equation problem quickly morph into problems that are only solvable numerically. Oh, mute that. In today's class, as I say, I'm going to introduce reading data and analyzing data. In the next class, we'll talk a bit about simulating data and visualizing data. We're going to be introducing some Python libraries, some Python packages. One of them we've already met, which is NumPy. The other Python packages that I want to talk about are the matplotlib package and the pandas package. So we'll meet those. I want to talk in the examples this week about actually scientific problems, but not physics problems. I just want to start us with scientific problems where we really know very little, have very little basis for those problems. And we'll see how we build models of those processes and how we read data in related to them, analyze data related to them, simulate data, and visualize data. And I've taken a couple of examples from climatology and ecology. So that's actually going to be this week. It's the only week I'm doing this. All the rest of the semester will be physics problems, but just for this week, and our first introduction to data is going to be more general science problems. Okay, so this slide is meant to be kind of an overview of modeling of physics problems or modeling of scientific problems in general, just sort of a conception of it. Typically, you would start down here on the bottom left and work your way clockwise around to over here on the bottom right. You would have some real life situation, some real life problem that you want to understand, comprehend. So is real life. You would make some sort of abstraction conception of that real life problem in terms of a model that contains the components, the parts, the pieces you think are important. So this is the model upstairs here on the top left. You would use that model to make some predictions, to come up with some results. And that's the box over here on the top right, the predictions. And then you could test that model against data, against the measurements for your particular problem, your particular situation. And so that's this this box down here on the bottom right. So we just went around the whole thing then, from the real life problem, through the models of the problem, through the predictions of the problem, through comparison to the data for the problem. The problem I was thinking of here, and the problem I'm going to talk about in climatology, is the problem of the thermodynamics of the Earth, temperature of the Earth. So we're going to make a model for the temperature of the Earth and make predictions for the temperature of the Earth and compare the predictions to experimental data on the temperature of the Earth. So when you think about this problem of what is the temperature of the Earth, you want to make some model of the important things that go into the temperature of the Earth. And so we'll make that model. The most basic things are shown on this little model picture upstairs here. Sunlight is shining on the Earth. That's energy that flows in from space to the Earth. So that increases the internal energy of the Earth. It would warm the Earth up. The Earth is a hot body. That causes the Earth to radiate into surrounding space, radiate infrared energy into surrounding space, and that cools the Earth down. And so a simple model might be, in terms of thinking about the internal energy corresponding temperature of the Earth, is the things that can change the internal energy and temperature of the Earth are the fact that there's sunlight shining on the Earth that is carrying energy to the Earth and would increase the temperature. There's infrared radiation being emitted by the Earth that's carrying energy away from the Earth, and that would lower the internal energy of the Earth and the temperature. So that could be our model. And based on that model, we would make a prediction. So we would use that model to make a calculation, or run that model to make a prediction. And actually it comes out to be, if we use this model, we'll say you get about 6 degrees Celsius for the average temperature of the Earth. And then you could compare that model with data on the temperature of the Earth. And here's just some data on the temperature of the Earth over 1,000 years, more than 1,000 years. And we could compare a 6 degrees Celsius estimate of the temperature of the Earth with this data here. So that's the problem that we're going to pick as an example. The example is ultimately going to introduce us to the need to reading data to compare to our model. We're going to want to read in fairly complex data to compare to our model, and how we might read that data in. And then also how to analyzing that data. How do we analyze that data? What methods can we use to analyze that data to compare with our model? So those are the steps we're going to make. Yeah.
I deeply apologize for being the complete lapse of judgment on my part. I hope I didn't miss much.
No, you didn't miss much, and it's in the campus slides, so you're in good shape.
Thank you.
Let's see. So here's the model I made for this particular problem of what is the temperature of the Earth, and specifically how can the temperature of the Earth change. And so the model is basically that here's the Earth, there's sunlight that shines on one face of the Earth that brings in energy to the Earth, can increase internal energy, increase the temperature, and then there's radiation, infrared radiation that's emitted by the Earth, that's emitted over from the entire surface of the Earth, and that carries off energy and will lower the temperature and lower the internal energy of the Earth. And out of that idea, that conception of the problem, I made something that's familiar from the last class. I could have made a differential equation to describe the problem, because we talked about that all last week. I made actually a difference equation, which we also talked about last week. Differential equation, we would naturally solve it analytically. The difference equation, it's natural to solve it numerically. So I made the difference equation. And this was my starting point. So let me just say a few words about that. What I was interested in is about if I've got the Earth, and I've got the Earth with a certain, at the moment, the Earth is bored, right? It's got a certain internal energy, it's got a certain temperature. It's experiencing this sunlight, and it's radiating this infrared. How's its temperature going to change? So I was interested in how the temperature is going to change. We said the temperature is going to change because the energy inflow and the energy outflow. And so I kind of wrote a equation for that. Again, I said, I'm doing this so that I could use it numerically in computational. So I've done something we did in the last class. I took continuous time and I turned continuous time into discrete time, where time just steps in little ticks from one tick to the next tick to the next tick. And I've labeled that as ticks in the equation with the subscripts I and I plus one, the two consecutive ticks. The change in temperature between two consecutive ticks here, tick I plus one, the future tick, and the tick I, the current tick, I've written down as this little equation. So this is my model. And this model has two intensities in it. Those are the uppercase I's. It's the intensity of the high frequency, short wavelength UV visible sunlight, that intensity, and the intensity of the low frequency, long wavelength infrared that the Earth is radiating. So that's the I sun and the IR here. Those intensities are watts per square meter. So they're joules per second per square meter. So they're telling us the amount of energy that's coming in each little, as a function of time, as a rate over time. There's one subtlety I put in here. I divided the sun's intensity by 4. And I didn't divide the infrared intensity by 4. The reason for that is the sunlight that shines on the Earth's surface, it shines really on a disk, the circular disk. That's the profile of the Earth to the sun. The infrared radiation that is emitted by the Earth is emitted by the entire spherical surface of the Earth. Now, the area of the disk that the sunlight arrives on is pi r squared. The area of the surface of the sphere of the Earth is 4 pi r squared. So the disk has a quarter of the area that the spherical surface of the Earth has. So sunlight intensity, I'm going to divide by 4 because it's effectively shining on 1/4 of the area that the infrared radiation is being emitted from. So these intensities are joules per second per square meter. So they're amounts per square meter, but I'm going to divide the sunlight's intensity by 4 and not the infrared intensity by 4 because the sunlight's shining on 1/4 of the area effectively that the infrared is being radiated from. So that's the 4 here. These other little bits here are the time interval and the specific heat, the effective specific heat of the Earth or the area of Earth that the sunlight is shining from and this infrared is emitted from. So remember that the intensity is joules per second per square meter. The temperature over here is Kelvin. So I'm going to multiply by to figure out the temperature change in 1 tick, I'm going to multiply by the length of time of 1 tick. And maybe that's a second, or maybe it's a day, or maybe it's a week or a month. If I multiply by that length of time, that's going to turn a joules per second in intensity into a number of joules. How much energy flowed in that time? The specific heat, division by the specific heat here, that has units of joules per Kelvin. So that's going to turn in the intensity, it's going to turn the joules per second into those joules into kelvins. So this multiplication and division is just so that I can turn joules per second in intensity into the change in temperature, the kelvins. And this is just an effective specific heat of the Earth. So I hope that's okay for the model. sort of two simple ingredients. It uses with the infrared and the visible UV. It uses the relationship between energy and temperature and specific heat. We had to build that in. There was this little factor of 4 that you better remember because of the areas over which the infrared and the visible light are either shining on or emitted from. I then replaced the infrared radiation, intensity of infrared radiation with Stefan Boltzmann law here. How it depends on temperature. So this is Stefan Boltzmann constant, and as you know, the intensity of black body radiation goes as the 4th power as the temperature. So this is the 4th power of the current temperature. And this is basically either a differential equation or a difference equation now. So it has like a delta T over here on the left-hand side, the change in the temperature, and it has the current temperature over here on the right-hand side. That's the uppercase T here. So if you want to check all these units, which kind of want to keep track of, these are all the units of the quantities that have gone into this equation down here. Anyway, that model yields if you solve that model, yields an equilibrium temperature for the Earth. And the equilibrium temperature for the Earth, it's kind of an obvious equilibrium temperature, is when the infrared energy that's carried off is equal to the sunlight energy that's arriving. So when those are equal to one another, that temperature is the equilibrium temperature, and the Earth will remain stably at that temperature. If we had started off with a hotter than equilibrium Earth, then it would cooled off at some rate to the equilibrium temperature. If we had started with a colder than equilibrium temperature Earth, then it would have warmed up to that equilibrium temperature, and it would have had a time constant that solving this equation numerically would have told us. Yeah.
So is the infrared intensity like in terms of can you write it in terms of the temperature?
Yeah, so this is the infrared intensity in terms of the temp. This is black body radiation.
Got it, okay.
So that is a key thing to put in and say that there's an equilibrium temperature. Yeah, so that's the crucial point here.
Okay.
The sunlight is, if you think about the sunlight, well, that's a measured intensity of sunlight arriving at our distance from Earth. But the infrared intensity, that's a highly variable thing that depends on the temperature of the Earth. So that's dependent on our variable that we're interested in. And so this difference or differential equation determines that pattern. So it's interesting that within this simple model, you come up with an equilibrium temperature for the Earth, what it will kind of equilibrate to. And it's actually a stable equilibrium. It's a stable equilibrium because if the temperature is larger than the equilibrium temperature, the infrared will be strong and it'll cool off because it's radiating a lot of energy, and vice versa. If the Earth is cooler than the equilibrium temperature, the Earth will not radiate much infrared energy because it's cool, and it will warm up from the sunlight. So this is a stable equilibrium. This is a case of negative feedback where you get a very stable equilibrium at the Earth's temperature. And actually, if you calculate it, so this simple calculation, if you just were to equate the sun's intensity, which we can measure, with this term here, the term you get from Stefan Boltzmann law, I already forgot the 4 here. There should be a factor of 4 in here. Then you get 6 degrees Celsius for the temperature, and that's not far off the global average temperature, which is about 16 degrees Celsius. We could make the model a bit more sophisticated with 2 key effects. One of the effects is that not all the sunlight that arrives at this sort of circular shaped disk is absorbed. Some of it's reflected. So there's reflection. So less sunlight is actually absorbed than the total sunlight that is impinging on the Earth. So the Earth will absorb less sunlight and less sunlight energy than the previous overhead. And the factor by which the Earth absorbs less energy is this factor on the slide. Factor A that's called the albedo. And so that reduces the absorbed energy due to reflections. The sunlight's reflected off things like ice. You know, the poles reflects a lot of the sunlight rather than absorbing it. Clouds reflect more sunlight. And so there's sunlight is reflected by various things, ice and clouds, for example, and this accounts for that. There's another effect. This infrared that's being radiated by the Earth. Well, that infrared radiation from the Earth's surface that has to travel through the Earth's atmosphere. And there are things in the Earth's atmosphere like water vapor, like carbon dioxide that will absorb infrared radiation. So not all the radiation is absorbed. Some of it is transmitted. Some of it is absorbed. And so that's a reason that less infrared radiation is emitted, and that effect will tend to warm up the Earth. And this quantity tau here is the transmission of the Earth's atmosphere for the infrared radiation. So a typical number is that the Earth's atmosphere actually only transmits about 70% of the Earth's radiation. So the albedo causes less, a bigger albedo, bigger reflection would cause less sunlight to be absorbed, the Earth to get cool. A higher transmission, that's the tau here, no, higher transmission would also cause the Earth to get cooler because more infrared energy is carried on. We can plug those, I've done it here on these two equations. I plugged in the albedo here, so it's going to reduce the intensity of light that's warming up the Earth. And I plugged in the tau here. This reduces the infrared radiation that's emitted into outer space by the Earth. And if you take these sort of measured numbers, these are typical measured numbers, approximate measured numbers here, for the amount of reflectivity of the Earth, about 30%. For the transmission of the Earth's atmosphere, and redo the calculation. I think if you do it with the best numbers that we have, you get about 16 degrees Celsius for the temperature of the Earth. So it's a little bit warmer because the absorption of the atmosphere is a little bit bigger effect than the reflectivity of the Earth. And so you get about 16 degrees, which is actually very close to the Earth's global average surface temperature, just by adding those two effects. So it's really quite a simple model where you can get pretty close to what the Earth's temperature it is. Again, in this model, right, this is if the Earth started off hotter than this equilibrium temperature, then it's going to cool down. If the Earth started off colder than this equilibrium temperature, it's going to warm up. There's a strong, because of this temperature dependence here of the infrared, there's a strong negative feedback that will cool down a hot Earth by radiating a lot of energy, or warm up a cool Earth by not radiating much energy. So that strong equilibrium is still here when you've got reflectivity and you've got transmission of infrared. If you wanted to do a more sophisticated calculation, and this is where this problem gets very interesting, and gets to be a problem that you can, only solve this numerically, is that you would take into account the fact that this reflectivity of the Earth and this transmission of the atmosphere are themselves temperature dependent. So A, which was just a number for reflectivity on the last slide, and tau, which was just a number for the transmission on the last slide, are actually temperature dependent. They depend on the temperature. And as an example of that, right? If the Earth's temperature was to go up, how does the reflectivity change? Well, if the Earth's temperature goes up, we melt some ice, we reflect less light. And so if the Earth's temperature goes up, the reflectivity goes down, we're going to absorb even more energy. And so that's a positive feedback that will take us away from equilibrium. So that's very interesting effect that happens because else ice will melt with increasing temperature. That's not negative feedback pushing us towards the equilibrium. That's positive feedback. Same sort of situation with the infrared transmission of the atmosphere. If the temperature increases, right, we get more water vapor in the atmosphere, we get more clouds in the atmosphere, we get more, or that water vapor clouds is going to absorb more infrared. So if the temperature goes up, we trap more infrared radiation. So again, temperature goes up, we get more clouds, we're going to have that positive feedback because the more clouds will trap more energy. And again, we got this kind of runaway condition. So those are the ice effect and the cloud effect are two examples of positive feedback in the thermodynamics of the Earth. And they are, to explore those, you have to explore those numerically. You can't explore those analytically. And they lead to a number of interesting effects. For one thing they do is they lead to you can get a situation of bifurcation of the equilibrium temperature of the Earth. And one way of thinking about the ice ages and the interglacial periods that we're in is kind of a bifurcation of equilibrium temperatures. And this bifurcation occurs because of these positive feedbacks rather than the strongly negative feedback of the dominant visible light energy in, infrared energy out. Okay. Well, that's just an example of how you build a model. And we're going to be building lots of physics models in this course. But I wanted to show you an example of, we don't know much about climatology, but we can build a simple model of the Earth's temperature and internal energy. If you made that model, what would you want to do? You would want to compare that model with actually the temperature of the Earth and how the temperature of the Earth is changing when the reflectivity of the Earth, that's changing too, when the transmissivity of the Earth to infrared, that's changing too. You would want to compare with data to see whether you have made a successful model or an unsuccessful model. And so this is, you look around on the web, there's lots of this data on global surface temperature of the Earth, on the reflectivity of the Earth, on the transmission of the Earth's atmosphere. So we can access this data. And when you're building a model, you often want to access data, read in data, and analyze that data. So I want to move on to now more practical case of reading in data and analyzing data and different ways we might do that. This is just an example of a file that I use that is online, and you can just read this file and read in data for the temperature of the Earth. And there are other files that contain albedo and contain transmissivity of the infrared. Okay. So I want to look at data in Python and how we might collect together data in Python. And I want to talk about 3 ways of organizing data in Python. As I say, we've just talked about a set of data that is temperature. The global surface temperature of the Earth over some period of time, many, many years in that table I showed you. There are a number of tools that we can use to read in data and work with data. We can use Python and its native tools. We'll look at an example of that. We can use NumPy and tools that it has. We'll look at an example of that. And we can also use a package called Pandas that we haven't met yet, and we can use the tools in that. So those are the tools for reading in data that I wanted to talk about. In the case of Python, the tool that we're going to use for storing data, like this temperature as a function of time data that was in that NASA file, is Python lists. So Python lists are native to Python, and we're looking at using Python lists to store some data. And reading data into Python lists, how we might do that. In the case of NumPy, we're going to use NumPy arrays, and we're going to read data into NumPy arrays and use that to view our data and analyze our data. And then finally, I'm going to say something about reading data into what are called data frames in Python that kind of resemble in pandas, which resemble spreadsheets. Just a few facts about the Python lists in this bullet, the NumPy array here in this bullet, and the panda data frames that I wanted to mention. So Python lists, I think of them like shopping lists. You know, they are a list of items like a shopping list, and that list of items can be integer numbers, can be floating point numbers, can be strings. All sorts of quantities can be in a Python list, and there's pros and cons to that. One thing about Python lists is that you can add to an existing Python list. You can remove items from a Python list. So that's one thing you can do with Python lists. There are a bunch of native functions that we can use on Python lists to analyze the data within Python lists. So that's another thing you can do. How about NumPy arrays? NumPy arrays, well, in that case, you can have one-dimensional arrays, like a vector. You can have two-dimensional arrays like a matrix. You can have higher dimensional arrays. And so that's a feature of Python arrays that might be useful for storing data. NumPy arrays. NumPy arrays are every element of the array is the same type. So if you have a NumPy array, all the elements are floats, or all the elements are integers. They're all one type. So that's a limitation with NumPy arrays. Another limitation is that you create a NumPy array, you can't append to it, or you can't remove individual items off it without copying it to another array. So there's limitations in being able to add to and remove from NumPy arrays. It does have, or NumPy has, a lot of useful functions for analyzing the data in NumPy arrays. So that's a value to it. Then finally, the Panda data frames. Panda data frames, just think of them as like a spreadsheet, like I don't know, an Excel spreadsheet. They have columns of data, and you normally have a header for the columns of data, just like a spreadsheet. They are what's called mutable. So if you have a Panda data frame, which is rows and columns with headers, you can change the order of the rows and columns. You can change the size of the rows and columns. You can add or subtract rows and columns. So you can change your spreadsheet with various tools acting on the Panda data frame. So that's useful. Okay, let's get out of that. Any questions on that? A little bit about an interesting model for thermodynamics and temperature and energy of the Earth to motivate us. But now we're going to move on to reading temperature data from a file into lists, arrays, and data frames, and see the pros and cons of these different ways of storing data. That's the plan. Okay, so here's let me make this bigger. Here's my Google directory with the Python codes I've been writing for the course. So here's the last couple of classes from last week. And these top three are for this class here. This data file here with this bizarre name to it is the data file that contains that data on the Earth's temperature that I showed in that slide earlier on. So it has quite a complicated format, the data in that table. It has headers. It has various entries that are not data. And so I took the data, I use a Panda data frame for that. I read this file and I turned it into another data file, this one here, which has a much simplified data format. Basically has two columns in it. Each column has one header. It's the year, column 1, and then it's the temperature, the global surface average temperature in column 2. So I made this file from that file, from the NASA file. I made my file. I made it to simplify the format so that we didn't have to worry about the details of the format in the NASA file. But I did that all with Panda data frames. I'm going to read data from that file into this Python notebook. And I'm going to read it in different ways. Let me just show you that the file. This was the original file on the NASA website. And this is the format of it. You can see that it's pretty complicated. It's broken up into pages that make it complicated and so forth. So I read that in and wrote this out. This is the file that is called global earth temperature.txt. That just contains 2 columns with a header on each column, year and temperature, and then a column of integers for the year and temperatures to 2 significant average global temperatures to 2 significant figures for that year in Kelvin. Okay. So this is my Python notebook that I made to read in that data and analyze that data a bit. I'm going to read in the data and we're going to read it into a list so we can play around with data in a list. I'm going to read it into NumPy arrays so we can play around with data in NumPy arrays. I'll show you how to read it into a Panda data frame as well. And when we read it into these lists, arrays, and data frames, we'll also analyze the data. Maybe we won't. I got in 140 years of global average temperature in this file. So it'd be interesting to know what the average temperature is overall. We can calculate that. And we could compare it with, remember, I my little model said that if I ignore reflectivity and transmissivity, the Earth's temperature should be 6 degrees Celsius. If I include reflectivity of the Earth and transmissivity of the atmosphere, 16 degrees Celsius should be the temperature. I could compare my model predictions with this world data. I calculate the average and compare it with that. I could also see things like how much does the temperature vary from year to year? What's the kind of variance or standard deviation, fluctuations of the temperature data? And is there evidence for the temperature changing over these 140 years? Is it increasing? Is it decreasing? I can look at all those things. Let's start doing that. The first thing I got to do is get the read in or access the data file. And here I've got a particular case where I'm using Google Collaboratory notebooks and like a virtual Google Collaboratory machine. And I want to access a drive, a cloud hard drive somewhere to read in my data. So I've got to integrate those two things. I've got to get those two things to communicate. My collaborative notebook on a virtual machine and my Google Drive, wherever that data is stored. And so I've broken this code up into cells to do different things. This is an example of where using cells can be really handy. So now I'm using cells in a sensible way. And this very first cell is really just about setting myself up so I can read in data into a file. So I think yeah, let me just go through this first cell then. So I've imported NumPy because we're going to use NumPy arrays. Yeah, make it bigger. Is that good? One of the things we're going to read the data into is NumPy arrays, so I'm going to import NumPy. Another thing that we're going to read data into is Panda data frames, these sort of spreadsheet. And so I'm importing pandas. And I'm giving aliases to NumPy MP and alias the pandas PD. So that's sort of familiar importing of packages, although one of the packages we know and one of them is new to us, maybe. These two lines here set me up for integrating my Google Drive with my notebook on my virtual machine. And so this is also kind of importing a package from this Google Collaboratory library. I'm going to import this module drive. This is the module that's going to give me access to the package. So this is very much like these imports over here. And then I'm going to use a method within that that module to mount my Google Drive on my to give it the notebook, my notebook access to that Google Drive. So this is importing a module. This is executing some function of that module. Just to show you that that works, these little commands here with the exclamation marks, these are ways of listing a file in your Google Drive. You might, if you use Unix or Linux, else will list a file in a directory. This is a way of printing a file. Again, if you use Unix or Linux, you would not be familiar with this for printing the file. So if I run this cell, I run that cell, it mounted the drive in those first two lines here. I asked it to list this file here. So this is on my Google Drive at this particular location in my Physics 508 directory. And then I asked it to print out that file. If you remember, that file contained a header of year and temperature, and then from 1980 on to current year or last year or whatever, the global average temperatures for each of those years. So we have connected to them. Okay, so let's go down to this cell here. Can I make it a little bit smaller? Is that still okay? So this cell I put in my reading of that data into a Python list. So that's this native list that come with Python. So that's what this cell is about. And when I read this, the data from the file, in this case, I'm going to read it in kind of what I would call a low-level reading of the data from the file, line by line, and picking out element by element from the line by line data. When we go to reading into NumPy arrays and panda data frames, we're going to use tools that kind of automate this. But I want to show you with lists kind of a more lower level operation on the files and on the lines of the files and getting in the data into our list. So I here I'm just declaring two lists. I'm going to make a list that contains the years, and I'm going to make a list containing the temperatures. And this is just how you declare empty lists with these two statements here. I'm going to then open the file, and I'm going to start reading line by line the file. So this function here, open, no surprisingly, opens the file. The two arguments that you see there are the first argument is the file path containing the file name and the file directory. And then the second item is the way in which you're going to open the file. I could open it and only allow myself to read it, or I could open it and allow myself to read and write to it. Here, I'm just going to allow myself only to read it, read only. So those are the two arguments here. File path, that variable, file path, I assigned it back up here as the string corresponding to the location of that file in my Google directory. So that's where I defined a file path. Okay, so here I am. I've opened in this statement here. I've literally opened the file, and the file is now represented by this variable f. You know, we had integers represented by a variable. We had floating points represented by a variable. We can have complex numbers, vectors, matrices represented by a variable. Now I've got a file represented by a variable. That file contains I know because I made that file, I looked at that file, that contains a header with some a description of the contents of the file. I want to, if I'm reading the data into a list, I want to make a list of the years, and I'll make a list of the temperatures. I want to skip the header, so that next statement will skip one line in the file that is the argument of the next statement. So that's just one way of skipping over the header. We don't want to try and put the string in the list of years and the list of temperatures. Now we got a for loop. Remember the for loop had in it two variables in the for loop format. The second variable here is the item that we're going to iterate through. That's the file name, and what we're going to iterate through is the lines of the file. So we're going to iterate on the file, iterate through the lines of the file, and for each line, as we go through this, each time we go around this loop, execute this loop here, for loop, we're going to get the next line. So we used for loop before, we iterated through, say, the elements of an array or the range of some integers. Now we're going to iterate through the lines of a file. That's what we're doing here. This is a function, the split, that is a method available for line. The line is a string, right, that we read out of the file. And Python comes with a lot of functions that you can use on strings, all sorts of functions, right? You can capitalize all the characters in the string. You can make lowercase all the characters in the string. You can do all sorts of things with native Python functions. What we want to do is that line contains two integers, the year and the temperature, and we want to separate that into a element of the year list and an element of the temperature list. And so we're fortunate there's this method, this function that will take the string in line, and if it sees them separated by some blank space, some white space, it's going to separate it into and return a couple of elements, and we identify those as the year and the temperature. So this picks out the year and the temperature of that one line. Then we said we were going to build the list out of the years and temperatures. So now I've got a variable called year that contains the 1 year on that line. I've got a variable called temperature containing the 1 temperature on that line. I'm going to add those to my list. I'm going to keep incrementing and growing my list as I go around this for loop. And so here I'm appending the year to the list. I'm appending the temperature to the list of temperatures. Now, when line got split into a year and a temperature variable, the year and the temperature variable, like the parent line, are strings. The line was a string and the year and the temperature are strings. When I'm appending to the list of years and I'm appending to the list of temperatures, I'm casting the string that is the year as an integer, casting the string that is a float as an integer. So I'm doing that here. And then finally, bookkeeping that and closing the file and shutting down the file. Okay, so at that point, we had two lists that contain the temperature data and contain the year data. And we've read in the data into Python lists. That's what we've been able to read in our data to the computer. I just want to show you a few things that you might do with lists. So this is a template for reading data into a list, is one thing I wanted to show you. This problem is coming up in this context, but of course, this problem comes up in lots of contexts. Reading file data into lists, this is a template for how you might do it. Look at some of the things you can do with lists. So look at this print statement here. The temperatures is one of the lists, years is the other list. But look, I can print out the length of the list. That's a native function in Python that works on lists. So I can print out the length. How many years do I have? I said it's about 140, but I don't know exactly. What is maybe this is not very useful for temperatures, what is some of the temperatures over those years? Might be if I wanted to work out the average, because then I could divide the length by the sum by the average, by the length and get the average. What is the coldest year? The minimum temperature? What is the hottest? The maximum temperature? I can use Python native functions min and max to determine those things. And so if I run that cell, those native functions that can take a list as an argument give me, let's see, let's print out down here. So I had 144 entries in the list. So I've got 144 years worth of data. The minimum temperature in the list was 286.5 Kelvin. And the maximum temperature in the list was 288 Kelvin. So there's a 2-degree difference for these global average temperatures over this 140 years. So we can see that. So it's analyzing the data. These are built-in native Python functions that can take list as an argument. List itself comes with methods that work on lists, that can manipulate lists. And typically they change lists. And already we were using one. Append is a method that you can use with a list to add data to a list. So we already use the list, append, as a method that works with lists to construct the list. Another example is pop. Pop is a method that removes items from the list. And pop has an argument, which is which item that you want to remove from the list. So here I'm removing the 0th item from the list. If you look down here, this printout, I printed out again the length of the list. It was 144 entries. I removed with this method pop the first entry, then printed out the length of the list again, 143 entries. So the append and the pop are kind of partners into adding to and removing from lists. Anyway, that's an introduction to how to get data into lists. Any questions on that? Okay. This cell is where I put all my code on reading data into NumPy arrays. In the reading of the file to put data in a list, I kind of did this low-level approach of going and opening the file myself, maneuvering myself through the file by skipping the header, reading the file line by line, then separating the contents of a line into individual strings on the line, and then populating, appending to the list. For the NumPy case, I'm going to use a NumPy method, and actually for the pandas case, we use a pandas method that is not so low level, right? It's actually built on those low level tools of opening files, closing files, reading lines, separating strings from lines. It's built on all that to give us a high level way of reading data from a file into, in the NumPy case, in arrays, in the pandas case, into data frames. So let's take a look at that. All that work in reading the file into the two lists of years and temperatures is accomplished really in this one line here for the NumPy arrays. it's a function in NumPy that's called load text. This is a function that allows you to read a file and read that data into NumPy arrays, for example. It's a function that has a lot of arguments, a variable number of arguments. Here I've just used a simple form of the function, which is 2 arguments. We've got to tell it the file path, which is the file name, and the directory, the string representing the file path. So one of the arguments is that. We did that before. And I'm also going to tell it a little bit about the file. My file, again, has that 1 line of header. So I'm going to tell it to skip that line of header with this argument in the load text function call. So skip rows will skip rows at the beginning of the file, skip the number of rows that you give it, that you set skip rows equal to, and I want to skip 1 row. So because I've got the header on 1 row, and so that's the way I tell the file to skip the first row. But anyway, calling this fills the contents other than the header into a NumPy array. Fills the entire contents of the file into 1 NumPy array. Now it's a file that is kind of 2 columns and 144 rows. So it's going to fill the data into a NumPy array that is 2-dimensional, with 2 columns and 144 rows. And it returns that NumPy array. So the data here is the 2D array, 2 by 144 array of those data entries in the file. Just like, lists, where there was some native functions that can act on the lists, and there are also methods that you can use with lists that act on the lists. There's similar things for NumPy arrays. We can use native functions on NumPy arrays to explore them, and there's a lot more. There's a lot of NumPy methods that we can use to analyze the data in NumPy lists. So I just want to show you a few cases of that. This statement here, this print statement, prints out some of the properties of this array. So shape is a method that will work on NumPy arrays, and so is size, so is data type. They're methods that work on NumPy arrays. They're part of the NumPy library. They tell us the shape, the size, and the data type. And if we look down here, this first row is the shape. It's 2 columns, 144 rows. It has a total size of 288 entries, and it's floating point numbers. And it is floating point numbers. And so those are some features of the array. As that line here. Now I'm going to go on and manipulate the array a little bit. I want to show you something that's going to be very useful for us. It's called slicing. It's used in the homework where you use slicing. It's a way of analyzing data in arrays. So this statement here, I'm going to take that 2-dimensional array that's called data, and I'm going to separate that into 2 1-dimensional arrays, one for the year and one for the temperature. Now we did this with the lists too. We read in a line and then we separated that. We split that into 2 separate lists. So again, I'm doing the same sort of thing. I want to separate the two-dimensional data array into two separate arrays for temperature and year. And I'm going to do that in this case with NumPy arrays with slicing. So slicing is something that you can do with NumPy arrays. This line here, it sets year to be this sliced piece of the data array. This specifies this slicing in the rectangular brackets. And it sets this variable here, the temperature, to be this slice in the data array. Now remember, the data array is a two-dimensional array, had 144 rows, and it has two columns. The description of what we're going to do with the rows is on the left-hand side of the column in the square brackets. The description of what we're going to do with the columns is on the right-hand side of the comma in the square brackets. So this is rows, columns, separated by the comma here. In the case of constructing the one-dimensional array of years, we want to pick out the first column. So I'm going to just pick out the 0th column. And this colon here picks out every entry from the first to the last in the first column. In the case of the temperature, I want to pick out the second column, that's the index 1. So this refers to the second column. And again, this colon, what that does is pick out every entry from the first to the last in that column. So this is me breaking data up into the 0th column, the first column, into these two one-dimensional arrays. If we plot the size and the shape of temperature and year after that, doing that, oh, it's actually on there. Now, the size of year is just it's a one-dimensional array. The shape of it was just a one-dimensional array with 144 elements, and the size of temperature, one-dimensional array with 144 elements. So we've accomplished that splitting the two-dimensional array into two halves, years and temperatures, by slicing. Slicing is something that we're going to get used to and do a lot. Here's another example of slicing. Now, I'm referring in that print statement just to the one-dimensional array year and the one-dimensional array temperature. And so I'm only going to refer to one index. I won't have a comma where we were referring to rows and columns. Now I've just got my kind of rows. Got the colon again, like we had up here. This colon, isolated colon, just picked out everything in that first 0th column, or everything in that first column. Now I've got a colon. I've got nothing preceding the colon, but after the colon, I got 4. What this does is this slice picks out every element of that array year, or every element of that array temperature, up to, but not including, this fourth element here. And if you look at the printout downstairs here, so we're going to print out the 0th element of the year, the first element of the year, the second element of the year, the third element of the year, but not the 4th element of the year, or all the other 140 elements of the year. So we just sliced out those 4. I just wanted to check they make sense, right? That's what I was doing here. Same thing for the temperature. It's now this one-dimensional array. This slicing will pick out from the first element, the 0th element, up to, but not including, this element labeled 4. So I get the first 4 temperatures of these first 4 years. And they're all about 287 degrees Celsius, Kelvin temperature. So that's slicing, and you'll use that in the homework. There's also one thing that's nice about NumPy arrays that's more flexible than a Python list is some of the methods tools that you can use with NumPy arrays. So remember, we were able to find the minimum maximum value of a list. We found the number of items in the list. There's many more methods for NumPy arrays. And here's just a few of them. And in this print statement, I'm just focusing on the array temperature. So everything I print out here is TP, the array that one-dimensional array that contains the temperature. I'm using a bunch of different methods. I'm using a method mean that calculates the mean of the list. I said I want to, what is the average temperature over the last 140 years, 44 years? So just tell me this. How much do the temperatures vary from year to year? Calculates the standard deviation formula. What is the variance? Square root of the standard deviation. Calculates the variance formula. What is the median, the most common temperature? What is the minimum? What is the maximum? What is not very useful here, but the sum. So I can print out all those things. Here's the mean, 287.1 degrees Kelvin. And so those first few elements are a little bit colder than that. Here's the standard deviation and the variance. So, you know, the standard deviation and the variance are fractions of a degree. So when you think about global averaged surface temperatures, the variations are small, fluctuations are small, and so on and so forth. I won't go through the whole list of numbers. Here's the again, the minimum and the maximum that we found with list methods also. The minimum was 286.5 degrees and the maximum was 288.2 degrees. Any questions on that? I think that one would be useful for the homework. The last cell that I wanted to show you was to read the data into a data frame. So this reads the data into a panda data frame, which is, I say, really like a virtual spreadsheet. So if you think about your Excel spreadsheet or whatever your favorite spreadsheet is, this gets the data into a spreadsheet. Again, it's very high level. So you don't have to open the file and close the file. You don't have to read the individual lines. You don't have to tackle yourself the headers or the whatever. You even handle, supposing you had a file, this file didn't have it, but you might have missing entries in a file. If somebody, instead of putting temperature, put that, not available, something like that. It has ways of handling those sort of situations, which it happens in real data, that you sometimes don't have values, or you have comments in the place of values, things like that. So it has all that. DF is the pandas data frame. It's the spreadsheet. Read, comma, separated version. That's reads a data file that is a spreadsheet with commas separating, but you can, that's one option in this. You can read Excel files, Google Sheets, all sorts of data. We've got the file path again. We've got a whole bunch, I'm not going to go through them, I just really want to show you this. A whole bunch of different arguments. If you went to the manual, you'll see a whole this list of arguments that will tell you how to all the options for reading data in. So this reads data into a data frame from that file. I printed out here the beginning of that data frame, so we can actually see the spreadsheet. But I also wanted to show you how you get the year and the temperature out of the spreadsheet. We use a data frame function that basically puts the data from a particular column labeled year or temperature into a NumPy array. So there's another way of reading the file. I'm ending here, don't worry. Here's the print of the header. Header is just a few lines at the beginning of the file. So the data frame contains the column headers. And it contains the data entries and their label, so it's a spreadsheet file. It's not NumPy arrays or Python lists. We can extract simple functions, data frame functions, the rows and the columns, etc., into NumPy arrays, for example. And that's what I did here. I made a NumPy array, an integer array that is the years, and I also made a NumPy array, the temperature, which is a floating point, so down here. Anyway, I'm going to finish there. I wanted to give you an idea about modeling, general scientific modeling. Today's class, we read in data, learned how various ways to read in data. That's very important in modeling. And we use some methods to analyze the data, simple things. You know, what is the average? What is the variance? What is the standard deviation of the data? In the next class, we'll look at generating some data with our model. We'll generate large volumes of data. And we'll look at plotting, graphing, histogramming, visualizing that data. So that'll be the second class of data. Any questions on all that?